Hi, I'm going to demonstrate the use of InterFringe to process an interferogram using spatial carrier analysis. Alright, I'm going to select this interferogram, and it has a very high spatial frequency of fringes across the aperture, and that's important because this technique requires the use of this high spatial frequency as a carrier wave for the irregularity that's contained in the deviations of those fringes, the phase variations. Alright, so first I'm going to define a boundary as usual. This is a synthetic interferogram. I created it from Zernike coefficients, so it's pretty idealized. It has 0.2 waves of spherical aberration, which hopefully we'll be able to recover in the process of doing this analysis. All right. All right. And here we go. Here's the spatial carrier analysis window. And there are some image processing tools here on the lower right that we're not going to need today. If the interferogram has poor contrast or has illumination variations across the surface that vary quickly, then it may be necessary to use these tools to improve the interferogram so that the technique works. But it's in general, you don't need to do that unless it's a pretty major issue with the interferogram. All right, this is the Fourier transform of the interferogram. You can see that there is a central peak, and this is an FFT which has had zero frequency shifted to the center. So this is zero frequency here. The two side lobes correspond to the positive and negative frequencies that correspond to the fringes in the interferogram. So I'm going to pick the top one, and there's no reason to pick the top one. It's just the one I'm picking first. I could pick the other one, but there's a relationship between the surfaces that you get from the two peaks. So calculate the wavefront here. You can see there's a little bit of tilt. That's the result of an inaccuracy in the centration of this boundary that I defined around there. The boundary has to be big enough to capture the important higher spatial frequency information in the side lobe, but not so big that it intersects a significant amount of the central peak. All right. Now, as a result, we're going to go ahead and calculate Zernike coefficients, and hopefully we'll end up with a similar result to what we started with. Now look at that, spherical aberration, 0.2 waves. So it captured that term. All the other terms are pretty small. There's a tilt term that corresponds to error in my centration, and then a piston term which is not important. As you can see, the Zernike polynomials, which go up to 37 terms for the fringe set, are all negligibly small, except for the one that we had specified as 0.2. All right, now let me pick the other maximum and calculate a wavefront from that. Now you might remember the previous plot showed an opposite curvature to this one. I'll put them side by side. Here's the first one. Here's the second one. You can see that the curvature is opposite. And that's the result of the two side lobes being conjugates of each other. All right, now there's one more thing that I wanted to explain. The nice separation of these peaks relative to the central maximum is a result of the spatial frequency of the interferogram, of the fringes. Nyquist frequency is at the edge of the FFT window. The Nyquist frequency corresponds to one fringe every 2 pixels. And so one fringe every 4 pixels should give us a very good separation, and that's a good rule of thumb. So it depends on the resolution of your camera as to what's going to give you the best separation. Let me open another interferogram. This one is not a synthetic interferogram. It's a real image, and it has a lower spatial frequency of fringes across the aperture. That's not a good thing, and I'll show you the result of this. I'm going to go ahead and define this boundary accurately. I don't know how accurately I am defining it. Okay, here we go. Okay, now we've got a boundary defined, and we'll go ahead and do spatial carrier analysis again. Now the FFT shows considerably less separation between these two maxima and the central peak. So I'm going to pick this one and define a boundary that's as big as I can comfortably make it without getting too much contribution from the central maximum, and calculate a wavefront here. Now the result is kind of muddy. It's got errors on the outside edge, and those errors come from the fact that there's contribution from the central maximum, and for the fact that we have not been able to capture all the higher spatial frequency information from the side lobe. This is not the best result. But we calculate Zernike polynomials, the annular ones, because we're dealing with an annular aperture. And when we do that, we can get rid of some of the noise because we're dealing with polynomial fit, and so some of the noise is eliminated from that with that technique. As you can see, as I scan the plot, there is an edge effect here, which is due to this error in the design. Basically, the spatial frequency of the fringes is not high enough. There's not enough tilt in the mirror. But overall, the result is still pretty good. There's still a pretty good characterization of the surface, characterization of especially the lower order terms in the Zernike expansion is all pretty good. So this can be useful even with the kind of error that we saw. It's still something that works fast and provides a lot of useful information. All right, thank you. This concludes the demonstration of spatial carrier analysis in InterFringe. Other features are demonstrated in other videos. Thank you.